Well, good morning, good afternoon, ladies and gentlemen. Welcome everyone to this online session where we talk about research and design tools to accelerate the growth of renewable hydrogen. And this is not just a normal webinar, really, because what we have with you today is if you are new to renewables or if you've been working in renewables, you for sure have heard of the National Renewable Energy Laboratories, so you would know how much of a leader and the leading role that they have in developing any kind of modeling tools, the new technologies, testing them. So they are really one of the main labs, that are working and facilitating and making sure that the know-how from renewables are transmitted to everyone and they're shared across not only the United States, but also internationally. So with the green hydrogen challenge that we have in front of us, I think it was a high time that one of the leading research institutions across the world looked at how to accelerate this growth and looking at how to facilitate the calculations, and the sort of working out the business models, the optimization tools that would help developers and EPC companies understand much better this technology that is new for everybody. So this is what we're going to be talking about today. And I have two people with me who you're going to meet shortly. But before we begin, I have a few requests for you guys on the other side. The first is please use the chat, introduce yourself, your company, and also tell us where you're joining from. Are you in the United States or are you maybe joining from elsewhere? I think, and I know that we have like a few, that we're a mixed group, but I'd like to hear where you're joining today so that we can see whether you're looking for some specific know-how or you have some specific questions and what sort of markets you're working on. So please just introduce yourself. Okay, I'll introduce myself in a minute as well. And I'd really like to have, thank you very much. Welcome everyone. I can see already that there are people in the US, but also in Israel. And I'm sure there are more in there, so please introduce yourself. So that is for the one thing is we have the chat there. You are welcome to talk amongst yourselves. If you're looking for something specifically, you're welcome to use it as well. But for the questions, and we do have questions because you're going to see a main presentation and then you're going to have the amazing privilege of having two NREL people here who've been working a long time in this design tools to answer your every need. So please send them, but please send them through the Q&A box that is at the bottom. So the chat box is on the side. That is for us to do a little bit of networking, even if we are like remote networking. And the other one is for your questions. And just to let you know, we are recording this session. So the session is being recorded and the materials that you're going to see, you're going to have access to. So you'll be able to connect to your colleagues, to everyone around you. And just one more thing, before I kind of stop my flow here and I introduce you to the actual panelists and the experts that are going to be speaking today, because it's not me, I'm just a facilitator. I just wanted to tell you that we are doing this webinar in the context of this event that we're preparing in Las Vegas. As you know, the growth of green hydrogen or low carbon hydrogen, or however you want to call it, in the US is going to take an acceleration and a growth of nothing we've ever seen before. I mean, the amount of money, of decarbonization interest that there is at the moment is just absolutely unprecedented. And hence, with this in mind, wanting to accelerate this networking, this collaboration, but also the understanding of the technologies as they are now and how they link up with the renewable side, this is what we're going to be doing at the event in Las Vegas. So I welcome all of you to look at the event, maybe to sign up for it, to come and join us, because there you will also meet Matt and Jen. So these are just some of the people. We have many more companies involved, but I think that it'll be important, that you come, you put a face to the name, and you start collaboration talks. So without further ado, I'm going to ask first Jen, just in the spirit of let's start with the ladies, to introduce yourself, and then I go to Matt, so you can get to know them better if you don't already. So Jen, tell us a little bit about you, what you do in NREL, please.
Hi, everyone. Thanks for having me today. My name is Jen King. I am a controls engineer at the National Renewable Energy Lab. I've been here for about 7 years. I work primarily on controls and optimization of hybrid systems, most recently looking at how do we scale renewable hydrogen to the gigawatt scale. And I'm very excited to be working with Matt on this project as well. So over to you, Matt.
Thank you very much. Matt, go ahead. How about you? Tell us a little bit.
Hey everyone, I'm Matt Kotarbinsky. I've been at NREL for cumulatively now 3 years. I support Jen King on a lot of different hybrid work, and then I have a couple other scopes within NREL that I do as well. So it's nice to see that we've got a good list of participants here today.
Yeah, and they're all over the world, if you get to look at it, but it's quite a few Americans too. So here we go. We are looking at then your research and your design tools. Matthew is going to be the one doing mainly the presentation. We have Jen there as a resource for anything. Jen, you and I, let's keep an eye on the questions. And if there is anything quick, we can answer it. So remember your questions through the Q&A box, okay? We take them seriously. This is one of those webinars where you get to ask the questions that you didn't think you could ask. So Matt, when you're ready, just put your screen, your presentation on the screen, and let's get rolling. And remember, we're recording. You will have it available. I always get asked that. I don't mind answering it again if you have the question again, but definitely you'll have access to all of this material, okay? So go on. You okay?
Yes.
Yeah, perfect. Now we can see it perfectly. So go right for it.
Awesome. Great. Thank you for that. Good morning, good afternoon, good evening. Thanks, everyone. Today, we're going to be talking about hybrid energy systems research. So this is going to include hybrids, HOPP, which is a tool that the hybrids group at NREL has developed, electrolyzers, and hydrogen. So we're going to be talking about a little bit of everything today. Here is our agenda. First, we're going to start off with helping define and understanding hybrid power plants. Then we're going to talk about the NREL design tool known as HOPP, followed by current green hydrogen research work that we're doing and we're wrapping up, as well as, I guess, current and what we're starting on, as well as NREL coordinated efforts within the H2 scope. So for some more context, here in the United States, the Biden administration, in conjunction with the Department of Energy, Interior, and Commerce, has announced a series of different targets. One of them is reaching full renewable energy by 2035 and industrial decarbonization, full decarbonization by 2050. Just to put this into context, if the United States was to meet the electricity target strictly with land-based wind, all of the land-based wind that's been commissioned between the 80s to now would have to be commissioned every year for the next 10 years. Now, of course, that's very aggressive and unrealistic. And so this is where hybrids can essentially help enter the conversation. Of course, there's another point there that we need, 5.6 times as much clean energy generation for even more context. And so hybrid power plants, it's a relatively new concept, and there are many different ways that hybrids can be defined. And so many ways that they can be defined, as well as many strengths that they have. And so you can see within the US, a large risk and challenge is transmission capacity and expansion. And so there are a lot of complications with that. And so with our working premise, we believe that we can meet 100% of these goals, at least the 2035 goal, with minimal new transmission. And that's a leveraging strength that hybrids can provide and offer. Another point here is hybrid power plants, whether or not you would like to see it on grid or off grid, can help avoid stranded assets. What they can do is they can leverage existing resources, and you can complement them so that you can, avoid the interconnection and transmission dilemmas. And so another point moving forward here is that clean hydrogen has a really interesting point to play here. One thing to note is with hybrids, they're a relatively new concept, and there's many different perspectives and how they're all defined. One thing that we want to mention is that hybrids at a minimum 2 generation points blended with either storage behind one interconnection point. We'll talk more about this later, but hybrids are very unique because they can be customized. And so what you can do is you can combine a series of different mature technologies, whether that's adding solar to existing wind, so solar under wind, and that works because of the diurnal cycle. You can also pair offshore wind with storage, and you can also develop new greenfield sites where you pair 2 generation asset types with storage. In this case, this would be a greenfield project. As mentioned before, a strength to hybrids is that they're customizable. And so you can customize them based on different end uses and purposes. And so in this example, you can see that you can provide baseload power with hybrids. You can also provide time-dependent power, so peaker abilities, and they can also offer different grid services. And so each of these different end uses will require different designs and controls. And so that is where the customizability of hybrids can be leveraged substantially. Additional benefits also include, firm power, so providing consistent electricity. There's also dual purpose end uses, whether that is the development and incorporating H2 production, which would be green hydrogen as we define it here in the United States. And then there's also other value streams as well, whether that is developing a hybrid facility that does have a direct air capture or carbon capture utilization storage component, as well as another thing which could be desalination. And so hybrids right now, even though they're the global perspective is in the process of helping understand what hybrids truly are, but we see hybrids right now offering 3 different services, which is your electricity services, your grid services, and conversion services. And so the key point here is with this customizability, if we can make electricity cheaper, then the faster that markets do become unlocked. A lot of the work that we've done at NREL has included a stakeholder engagement and market analysis outreach to understand. And there are different industries, especially those that are heavy industries or difficult to decarbonize, that have customers that do demand green alternative products. And these stakeholders and these businesses are interested, but for them, it's a business perspective. And if it makes economic sense from a business perspective, then new markets can be further unlocked in that regard. So now that we gave some background and context for hybrid power plants, now we're going to pivot and give some context into the tools that we have and how that works together with hybrids as well as hydrogen. This tool that the hybrids group at the Flatirons campus within NREL provides is called HOPP, or Hybrid Optimization and Performance Platform. And so this was a tool that helps optimize co-located utility scale hybrids down to the component level within different markets. And as you can see here, there's essentially 5 different components that make up hybrid as a whole. So you have your generation component, your storage, controls, markets, and end uses. You can see all of the ones that we currently provide, and then important to note that each one of these has a custom option. The cool thing about the hybrids group and HOPP is that it is very customizable. And if there's a component or an input that we don't have, we do have the capabilities to work with partners or organizations to help create a custom feature that can help quantify and give as optimized and accurate results for specific end uses. And if you look all the way to the right, you can see that there's an H2 component there, and that is something relatively new within HOPP that we call H2OPP, which is essentially the hydrogen component within HOPP. And so simply put, the goal behind HOPP is to help answer the question of when and where do hybrids make sense and how can we design them optimally. And so that is the motivation behind HOPP. Okay, and to talk more about HOPP, HOPP is integrated with other tools and resources. So HOPP does have a location component, which then also leads to wind and solar resources. So we use ReOpt on a system level design there. Then what we do is we go down to a more detailed component level where we look at the plant itself and we look at a component level to help customize specific features, inputs and outputs, if you will. So that includes specific wind turbine data, solar panel data, batteries, storage, hydrogen production component, performance and cost. And then as you see there to the right, we also have a NREL H2 analysis tool that's been incorporated, which is that H2OPP hydrogen version of HOPP. Now, I don't want to spend too much time on this slide. The reason that we have this slide here is to give you an example of a type of result that you could expect within HOPP. And a couple of things to note here is the fact that this has a wind component a solar component, and a battery component. And so you can see the capability that HOPP has based on the series of inputs that the user would give, based on your type of technology that you want incorporated, as well as geographic specific characteristics such as wind and solar resources. And so this right here is a perfect example of kind of forecasting into the future to give you an idea of what your theoretical use case facility could do with battery charging and discharging, as well as potential curtailment events. I'm not sure if we wanted to stop here for questions before we pivot into the next section.
No, I think continue, Matt. There are some questions, but they're quite general, so we can get to it at the end. Thank you.
Awesome, great. So now I want to start talking about, hybrid power plants and green hydrogen. So this is essentially kind of highlighting currently the nexus of NREL work that takes your new technology concept with hydrogen. I wanted to bring back this slide here because I wanted to focus on the center box here, if you will. For this, this is where we are really focusing on hydrogen production. And so what we're going to be looking at is different examples of projects that we have been conducting and we're now wrapping up that does demonstrate all the different components that we are currently taking into consideration. And of course, green hydrogen production is now very in high demand. And so a lot of attention and resources are going into this. And so hopefully we can give you an idea of what we have been doing as well. The first project that I wanted to talk about is what we essentially have been calling wind H2 systems. This project was very interesting, and there's a lot of unique components that we've been taking into consideration to help essentially kind of ensure that we have different future outlooks for different scenarios. And so for this project, we looked at on-grid versus off-grid systems for hydrogen production with wind. We also have a hydrogen production component, as well as ensuring that for this research, we have optimally designed these different use case examples to ensure as low of an LCOH value as possible. And so we have kind of analyzed all these different configurations and different use case examples. So within this example, something to note is there's a lot of information on this slide, but this is a perfect example of how we are using HOPP to help optimally size your electrolyzer within your use case design. So for this example that you're looking at here, I really want to focus on the chart on the left. So this is showing us if you have a 150 megawatt rated wind facility and you pair this with a 50 megawatt electrolyzer, what does this do to your hydrogen end use value? Now you can see here, if you have a 50 megawatt electrolyzer, your LCOH is almost $7 per kilogram of hydrogen. Well, there's a lot that can be taken away from this. And so in short, your electrolyzer is too small because you're having to curtail excess energy that could have been used to produce hydrogen that is not. So that's one example. But then the question is, well, what happens if you double your electrolyzer size? Well, when you do that, your LCOH value drops almost $2.50 per kilogram by increasing your electrolyzer sizing by 50 megawatts. And so you can see here that, yes, your LCOH is lower, but you're still not maximizing or optimizing your theoretical use case here of your 150 megawatt rated wind facility. Now, if you match your electrolyzer sizing to the same as your wind facility, your LCOH, you can see it's $3.84, and you're almost utilizing your energy that's being generated. But then the question is, what happens now if you oversize your electrolyzer more than what your nameplate capacity of your wind facility is? And now at this point, you start to see that your levelized cost of hydrogen starts to rise incrementally again. And that's because now at this point, you're not using the entire capacity of your electrolyzer. And so I wanted to highlight this example because this gives you an idea of what this HOPP tool can be used for in when sizing a facility for whatever your end use may be. Another example that I really want to talk about is circling back to the Wind H2 piece. And before talking about that, I did want to, acknowledge and recognize the Inflation Reduction Act. The Inflation Reduction Act is a huge game changer. There are a lot of different provisions or tax credits within this bill that help reduce end-use costs. And so you can see here, we've got a table of different policy scenarios that we have used within different analyses within our work. Now, the reason why we include all these different scenarios is just to show the impact that policy can have on end-use values, and also having a no policy scenario to give you a performance technology baseline. And so then what you can do is compare the different values there. And so within our research, the three common scenarios we do use is the no policy, followed by a policy scenario that we've been calling as base, which is your lowest 100% value of your PTC and your ITC. And then of course we have a max or bonus scenario, which is a combination of including your prevailing wage and apprenticeship 5x multiplier, as well as the different bonus credits as we deem them applicable to our use cases. Another interesting and very unique thing is the stackability of these tax credits within our use cases. We recognize we're at this really interesting point where there are credits and there is still a lot of uncertainty as to how the IRS will be approving or how these different credits can be applied within a use case for a taxpayer. So that is definitely an uncertainty. And so we're working as best as we can to ensure that our inputs are as accurate as possible. And then, as I mentioned before, we have other additional considerations, such as your prevailing wage, your different domestic content bonus credit, which is sourcing materials made in the US, steel, and then your energy community bonus credit as well. And then the last point there is your carbon capture, utilization, and storage credit. We've got that one mentioned there, but we can talk about that more in a few slides. So this is the first example of our wind to H2 analysis. This is a nationwide analysis from years 2025 to 2035. And so this is a no policy example. As you can see, this is a little GIF here. So you can see how the values change over the span, and the break-even point where the colors transition from blue to red is your $2 per kilogram. And you can see this is just a very unique visualization. We do have numbers, but we cannot release them yet. So we just wanted to include this visualization to give you an idea of values over the next decade or so. And another thing to note is that this nationwide analysis had a baseline of a 100 megawatt wind facility as well as a 100 megawatt electrolyzer. This is the base policy example. And you can see how there's a lot more red, which means you are now under that $2 per kilogram threshold cutoff. And so for the base policy example, we did take our 0.3 cents per kilowatt hour. And then we also took the clean hydrogen credit. And of course, we ensured that everything, the values are adjusted appropriately for inflation as well. And this example also uses the 100 megawatt wind facility as well as the 100 megawatt electrolyzer. Next, what I'd like to talk about is kind of the current research we're looking at. But before I do, I just want to check in and see if we happen to have any questions.
Yeah, we have lots actually, Matt and Jen. If you want, we can answer some of those. Some are about HOPP, but they came later after you. So we can start with those. And some of them are, there are some that are a little philosophical that maybe we can leave those for later, But I think the ones about HOPP, it would be better if we answer them right away. So one of them is HOPP a free tool? Hang on, let me get you. Do you mind if we get this off the screen so we can see you better now? And then we can go back to the screen, Matt? Yeah? Okay, sure, here we go. Okay, so one of the questions here says, is HOPP a free tool? Can people use it?
Yes, I just want to see if Jen wanted to answer.
Is the question by Mark Triplet?
I put it in the chat. Yes, it is. And it is on GitHub. We have several branches for several different types of technology, so feel free to get in touch with us for what branch you should be on and where that data lives. I did see some reference to like CapEx, OpEx costs for electrolyzers and things like that. That does exist in the repo. We can put you to those.
Okay, so yeah, I was going to get to that. One of the other questions says, how does HOPP, or HOPP, compare with Homer software for optimizing microgrids and distributing energy resources? Homer is very well known in the industry, as you know.
Absolutely. Yes, we've done comparisons with HOPP, so with Homer, excuse me. Homer's traditionally come from the distributed side of the house in the microgrid space, and has moved into the utility scale space as well, with hydrogen even as well. I think the limitations we saw from using that was getting down to the component level. So how do you design all the way down, like how many turbines are you can have? What's the size of the turbine? What's the size of the electrolyzer? How do you control the electrolyzer with respect to the turbine? How do you control different stacks, different amounts of stacks? And those types of questions we had a little bit of a challenge answering in the current landscape. So that's why we've developed HOPP to be able to answer those more detailed design-oriented questions. And the other thing that we address that is really critical for these systems, I think, is the tightly coupled co-located bit that Matt was talking about. So this is really HOPP really does well on co-located systems. So hiding behind a single interconnection point so that you really maximize that use of an interconnection point, and you're taking advantage of similar systems. You can take advantage of balance of system. You could take advantage of power electronics, shared controls, shared management structures, that kind of thing. So HOPP provides flexibility to address some of those things. They're challenging, but that flexibility really helps us dig into that. And we have some examples on the repo regarding those questions.
Considering how difficult permitting is at times, getting interconnection points, I think it's very important that you maximize as much as you can, what happens like before the connection. Okay, thank you very much. And shall we look through here? There is still a few much. One is, Angus asks, which geographies does HOPP currently cover? Is it the US only, or does it include international data? It's Angus Mattison, yeah. Matt, I think that you've been told to answer this if you can.
Yeah. So right now, it is US focused, just because I think of just the organizational structure that is NREL at the time right now. However, right now it's US based, but I do believe that there's always an opportunity to expand this resource internationally as well.
Yeah, and it's more oriented if you can write a wrapper for your resource files, then you can use HOPP.
Does HOPP software solve for the lowest LCOH? Although, can you imagine understanding what this means depending to the regulation? Have you seen the latest map that Matt showed like literally a minute ago? I don't know whether, I guess the regulation is not taken into consideration in your calculations, right? It would be purely technical calculation in HOPP.
I'll take a first attempt at answering at least maybe some of this question. I guess, yes, there are components that are not yet incorporated in full detail, just as a result of kind of how the geographic landscape of policy has been shifting recently. However, there is a lot of interest in internal conversations into embedding a lot of these other considerations within this, as long as it's within the means of our research budgets and all of those things.
Okay, continues if you like, Matt. I'll continue. Here they're asking me, where is the CapEx and OpEx costs for the electrolyzer coming from? Are these available in the HOPP GitHub repo? So is this what you just answered, that they are available? Or okay. And how can you download or access it? You send the link, correct? So this has been done, okay? You guys, like seriously, we're on a roll today. You're literally answering everything, and it's all great. Again, as asking whether it's a free software, which it is, right? Or does it have a cost? Yeah, it's free. And does HOPP integrate with SAM? And do they provide similar potentialities? I kind of was laughing when I read this because this is the same thing that I asked these guys when I met them. You know, how does it compare to SAM? So can you tell us a little bit more about how does it compare to SAM and how do they sort of help one another?
I'll pass that one off to Jen.
Okay. Yes, SAM was the main driver, our main engine for our technology and cost modeling for individual technologies. In the beginning, as Matt talked through HOPP, we have a way to bring in different types of models. So for example, SAM has wind. So we have used the wind model there in the past as well as the solar model. But recently we've pivoted our wind model to our florist model at NREL because that gives us a little bit more controllability around that based off of our research. And so we've kind of pick and choose which SAM models we use, I guess is the long answer to that question.
It's not that long, Jen. You're doing really, really well. Thank you very much for being short and sweet. Okay, so just a couple more and then we can continue, okay? And we'll come back because a lot of these questions are a lot more wider. And then I think, you know, we bring out there. Well, I think, you know, so, but for now, I just thought this we can get out of the way. Lee asks, is HOPP easy to use or is it a complicated program with a steep learning curve?
As it exists today, it does have a steep learning curve. I would say it has been born out of research. We have plans to have that simplified and remove that barrier to entry by September of this year. So we are doing a rewrite at this point. So stay tuned if you want to wait for that version. But yeah, we understand that that's a huge barrier.
I mean, honestly, it seems like a small price to pay, you know, when there is so much potentiality in this tool specifically, but it always helps when there is a little bit of like UX. So thank you very much for reviewing that, guys. I know it can be easy for you, especially scientists, you know, because it's just easier in some ways to add complication and complexity because that's the nature of many of those projects. So, and Rodri Hawkins is asking regarding H2OP. I think they mean HOPP. How does, but this is a great name, by the way. You should actually patent that and call it H2HOPP for the for the name. How does this improve the current state of the art for design, evaluation, linear time independent like OEMOF or MVS for dispatch? Honestly, I don't know what this is, so I trust it's just some tools that are very specific. Or robust design, for example, a generic based design with deterministic import-export rules. Is the question from Rodri.
Great question. Matt, do you mind if I jump in really quick?
Not at all.
Okay, I might need some clarification here. Apologies for that, but I think what we're getting at here is because HOPP gets down to that detail level, you can start looking at the operational strategies and how things might be able to be changed so that you can maximize the lifetime of your assets while producing as much as possible. So for example, one case that we've been looking at recently is conversion efficiency. So let's say you have a gigawatt scale electrolyzer. Should that be one big giant gigawatt scale stack? I know those don't exist today. But should it be that, or should it be a bunch of smaller stacks that you can kind of turn on and off? What works best with current renewables? We've heard anecdotally that if you just bolt an electrolyzer to a wind turbine, that drastically reduces lifetime by 60–70% potentially. And so having the ability to control different stacks at different levels instead of averaging them all across all the stacks might be beneficial. That's something we can do with HOPP. And so we aren't only held to the current import-export rules, I think. And that's what gets back to HOPP looking at tightly coupled co-located systems. That's really the bread and butter. So we're taking advantage of the fact that those systems are co-located and that we can coordinate the controls across technologies.
Okay, thank you very much, Matt and Jen. You've just had like a rapid fire session in there. I think we've done like almost 10 minutes, so a little bit less, but like of questions. So if you like, Matt, why don't you continue? We do have, as I said, some wider questions, but maybe we can tackle them at the end, and it'll be hopefully more that will come in the time from here to there. Okay? Excellent.
That works for me, and I'm sure we'll have more questions for this next section, or maybe. You know.
There are more for HOPP now, so Jen, you're not off the hook yet. Sorry. Keep going.
Alrighty, I'll make sure to resume sharing my screen here. Alrighty.
Yeah, perfect.
So moving along, this is now looking at current research that we're looking at. So what we just kind of saw and what we just presented on was focused on wind H2, so land-based wind. Some ongoing work that we're currently looking at is now pivoting that scope to offshore wind. And so this is what we've been calling offshore wind H2. And within this project, what we're doing is we're incorporating different models within NREL that do add that offshore wind component. We're also looking at fixed versus floating systems. And we're also looking at what is the most economic way of moving energy, whether that is through pipelines or through cabling. This is a visualization of our case studies, if you will. And so we chose 4 locations that are receiving a lot of interest for potential offshore wind sites. Whether that's the upper Atlantic in the Northeast, California in the West Coast with potentially floating offshore wind, and then the western portion of the Gulf of Mexico. Of course, with the Gulf of Mexico as an example, a lot of the better wind resources are in the western region, and so that's where there are call areas and a lot of interest in development of offshore wind systems to some capacity. And so as you can see here, California is using floating, and then the other 3 locations are using fixed bottom. Moving along, for this analysis, there are different ways of moving energy to shore, and there's also different ways of producing energy and then moving it. For this project, we have 2 different configurations, where configuration 1 is we're using cabling to move electrons onshore to then support hydrogen production and then storage there and moving along those lines. The configuration 2 is where there is a centralized platform offshore, and then there's a pipeline that moves that onshore. And so, of course, there's different challenges to utilizing pipelines and cables. And so the point of this research is to really help gain insight and understanding into what would be more optimal, and also just kind of understanding what challenges are associated with these different configurations, if you will. So as mentioned, the analysis for this project is currently underway, but the trends right now do align with other scenarios where it seems that pipeline transport is more economically competitive when compared to cabling. And also the other component here is storage is crucial, both for offshore wind and land-based wind, and that storage component can have a really big impact on your end use value. With this project, there's a lot of work that still needs to be done, which includes kind of transmission studies, looking at cost-effective ways of moving hydrogen to shore, storage options. As mentioned before, storage is crucial. And then also kind of understanding how code generation with other generation assets can play in and impact end use values. Of course, there needs to be more coordination of different studies to kind of understand the accelerated deployment potential. Of course, for example, the Gulf of Mexico region has heavy presence from other energy industries. So it's also curious to see if there could be some synergies there to see if that can help impact lower end use costs as well as distribution. And then of course, supply chain constraints as well. And using Gulf of Mexico as the example again here, there is a heavy industry presence there already, and the conventional energy presence has already supported other renewable energy sectors, such as with the foundations that were built in the Gulf of Mexico that were then used for the Block Island wind farm, which is the United States' first offshore wind farm rated at 30 megawatts. This next project is looking at gigawatt scale wind H2 end use systems. Now, of course, this goes back to how hybrids can help and can be leveraged to achieve the different targets that the US has announced. And as you can see down below here, the 16%, the 24%, these are all total percentages of emissions in the US. And for example, if we are able to help decarbonize heavy industry, such as green steel, then you have, in essence, cut out a quarter of US emissions. And so we do recognize that there is no one silver bullet solution, rather there are many, and hybrids are seen as one of these, and also the case of green hydrogen is seen as a unique catalyst in decarbonizing these heavy industries as well. Moving along with this project, we've been calling this project industrial decarbonization, green steel, green ammonia. And so the vision of this project is to look at gigawatt scale projects, on-grid, off-grid, purpose-built, and optimized for low LCOH and co-located near steel and ammonia production. So this is kind of looking at decarbonizing the steel sector. This project is really unique because we're looking at optimizing LCOH, and by optimizing that, helping reduce the cost as much as possible and exploring all different configurations and plant use cases that can be leveraged for this type of future outlook within the achieving these targets. For this, we're also taking a holistic approach. We're looking at increasing efficiencies and reducing capital costs. And with hybrid power plants, there's a lot of different synergies, and we'll learn about those in the next few slides there. So that's a little bit of a foreshadowing. And then also having independence from natural gas prices, supply chain shortages, materials, and also removing the dependency on transmission build out. Because, for example, if you wanted a grid connected system, then there's other wait times that are essentially out of your hands, regardless of how quickly you build your facility. Wait times for interconnection can be anywhere between 7 and 10 years for an on-grid facility, and then off-grid, your only timeline there is how quickly it takes you to build your facility. So, of course, the goal of this is to understand how can we essentially achieve economic feasibility for a 1 gigawatt hybrid energy system to then produce hydrogen for green steel and ammonia. The high-level system configuration for this project, we do have a baseline case, which is essentially how everything is operated currently. We have coupled co-located examples as well for on-grid, and then we also have a similar use case design, but off-grid as well. So we, for this project, are exploring all different use cases to help kind of identify what could be a very cost-effective way while decarbonizing the steel industry. For context, this is how things are currently done, where you are utilizing the grid. The grid is everything in that red text box there, and there's a lot of complications. By doing this, there are different losses as well, and potentially sunken costs. Your efficiencies decrease, and there's complications there as well. And then, of course, then you have the argument, if you take your clean energy, put it on the grid to then pull somewhere else, is it actually clean electricity that you are utilizing? So there's a lot of complexities here. And so what we're looking to do is essentially eliminate everything in the middle. And by eliminating that, then you're unlocking a lot of different savings and efficiencies. So, you're reducing and essentially eliminating capacity queues, energy losses, and then as a result of having a hybrid system, then you are sharing power, electronics, and controls, which is additional unlocking of cost savings. And essentially what this means is all these cost savings and reducing any redundancies ensures a lower end use cost. whether that is your LCH or your cost of your green steel product as well. This next slide is a visualization of one of our use cases. I'm not going to go into the details, but I really want to use this as a kind of a shock factor to show you all the different components and considerations that are utilized. And then another thing to note here is in the center right here, we also, for all of these different scenarios, looked at all the different provisions for policy from the Inflation Reduction Act. And we have those toggled on and off to also see how big of an impact policy has on these use cases as well. This tool, this slide deck right here, this slide, more so we want to use to show how spatial variability can impact end use costs. Now we have 4 different examples here. We have Iowa, Indiana, Texas, and Mississippi. All of these have been chosen because they have different considerations and characteristics that could impact end use costs. Iowa, for example, has really great natural resources. However, there's no geologic storage, and it's also close to demand, and there is a existing infrastructure there. Indiana has a large steel mill. There's no geologic storage. Texas has salt caverns as storage options. However, it's a water stressed region. And then, of course, excellent natural resources, wind, and then solar for West Texas as well. And then lastly, Mississippi, which has access to salt caverns for storage, is close to existing demand, but of course does not have any natural wind resources. And so we wanted to show this as considerations that we are looking into to understand how all of this could impact end use costs of hydrogen, and then subsequently steel. So here, we don't have detailed numbers. We also want to use this as a visualization tool to show the different use cases that were modeled for this project. And of course, we have policy toggled on and off to show you big cost savings from policy. And so for the policy component, we have considered the carbon capture utilization storage credit, your production-based tax credits, whether that's for wind or your clean hydrogen production credit. And then we also have looked at the investment tax credit as well. And we have applied these for all components within the facility where it is applicable. And of course, there's a lot of complications with stackability, which is also why we have all these different examples here. So we have SMR with carbon capture storage, grid only, grid plus renewables, and then off-grid scenarios as well. So you can see here, of course, the goal is to be ensuring consistent hydrogen because that's the demand that's needed for the steel industry. So yeah, it's a nice little visualization there. Moving along, this is another visualization that we wanted to use. We wanted to show you the 4 different states for all the different technology years, how costs can add up to then result in different LCOH end use values. The big takeaways here is essentially Texas achieves the lowest cost of hydrogen. Iowa has amazing wind resources, but lacks access to low cost storage. And then Mississippi doesn't have great wind resources, but it does have access to low cost storage, which is your lined rock caverns. And so here you can see 4 different examples. One of the biggest differences is storage. It's storage that really impacts your end use value. And it's not just any storage, specifically it's your lined rock caverns, because above ground storage is an option. However, it's expensive and it does impact your LCOH to the point where then it gets a little tricky to see whether or not your hydrogen at that point is cost competitive. And then just kind of talking more, focusing specifically on Iowa. Now, Iowa does not have close access to good storage options. And so this slide shows, well, what happens if you pipe your hydrogen 400 miles north to your closest lined rock cavern storage? And it's really interesting insight. You would think that such a long pipeline could be very expensive, but that is still cheaper than if you were to build above ground storage on site. So this really does give some interesting insights. And this kind of is interesting to see how this kind of plays in with offshore wind to H2 systems as well. But as you can see, yes, the lined rock cavern storage is about $29 per kilogram of hydrogen compared to other options, whether that's in South Carolina or above ground. As you can see, there is about $540 per kilogram of hydrogen. And of course, as I mentioned, even if you pipe your product 400 miles north, it still allows for economically competitive H2. And so low cost storage, as I mentioned before, is equally as important as other components within your facility that then dictates your end use costs there. Yeah, it's really interesting stuff. And this is essentially just giving a project overview of this industrial decarbonization effort, where phase one was, assessment and analysis to, identify and determine pathways for low LCOH and green steel costs. Phase two is system design and control. And then phase three would be a demonstration plant and facility. During this effort, when we reached out to industry, right now that we're at this interesting point where there are a lot of different stakeholders, whether that's industry or academia, that are all looking at having 10 megawatt scale demonstration projects with a gigawatt scale or 2 project announced over the next few years. And so what we are going to be doing is hoping to achieve that, where we can help validate some more information. So I have one more slide, and I know that we're kind of creeping up to the top of the hour here. So the last thing that I'd like to close out with is essentially just kind of highlighting some of the global green hydrogen efforts and coordination that NREL is currently involved in. And so Jen and myself are currently involved in IEA Task 50, which generalized is focusing on hybrid power plants. There's a series of different work packages within them, and one of them, work package 1, is also developing and collecting a general consensus on how to define hybrid power plants, not just from one perspective, but universally and globally. And so this effort is to coordinate research and development on hybrid power plants, whether that's taxonomies and definitions, reference designs that do have that hydrogen and electrolyzer component in them. And there's a link there as well if anyone would like to check that out for some more information. Other tasks is NREL is also involved with an H2-based IEA task. This task is very early on in the development, so conversations are currently being made to establish that task specifically, but that does have a wind, solar, and hydrogen component as well. NREL is also going to be the chair for a Wind H2 session at WESC, which is the end of May in Glasgow, Scotland. And then here I have 2 project collaboration examples as well, where there is an NREL and TNO techno-economic analysis comparison study. And this is to ensure that there is alignment on offshore wind H2 research in hopes of identifying uncertainties, barriers, and also potentially validating different assumptions based on how early this kind of concept is. And we're hoping to have public results by the end of the summer, potentially early fall. And then the last project here is called H2 at Scale. And this is developed to understand what happens when a turbine is designed specifically for H2 production and prioritizing low LCOH values. And so partners for this project do include GE as well as NEL. So with that said, thank you. I know there's a lot of information. So I guess we will take questions now.
Yeah, thank you very much, Matt. If you stop sharing, we can see you bigger than I think you and Jen, which I think it's more useful at this point. We have a lot of open questions, so I'm going to encourage you to take a look and see if there's any specifically that you want to answer, because we have 5 minutes. Even if we take an extra 5 minutes, we're not going to be able to answer 18 that are open.
Sure.
I'll start with some, okay, and some of them are not too complicated, so maybe we can. There was this one about whether you account for electrolyzer efficiency variance per load ratio, ramp-up constraints, startup time. And I can see Jen going like this, so that means yes, yes?
Yes.
Okay.
Yeah.
All right.
Yeah, that comes into play in our control strategy for how we manage electrolyzers right now. If you just directly connect wind to electrolyzer, we know that that's not the optimal solution because it's going to degrade your electrolyzer super fast. Connecting to the grid is an option, but that brings other constraints. It's dirty power in some sense, and you have to pay for retail rates. The other question I thought too was around distributed hydrogen. So if you were to pair an electrolyzer with a turbine, that is an issue. You're not going to increase your utilization of your electrolyzer unless you have a battery there. We haven't found that to be perfectly cost effective at this point. In the analysis that Matt showed, we did use for the off-grid cases a reduced lifetime, but we used it for the centralized location. So all of the wind is coming into the one electrolyzer versus the one electrolyzer per turbine. But we didn't vary it much from there. So that is definitely an open question for sure. So
the question that you're referring to now is the direct coupling question, right?
Direct coupling, yeah.
Yeah, okay. I just wanted to check because so that I know that this has been answered and I don't ask it again. Someone here asks whether you integrate energy market information. For example, the states that don't allow to self-generate, it does. Seriously, like, I can't believe this is for free. Seriously, usually you'd be paying a lot of money for this. I know that there are other tools out there, but this is really pretty amazing.
The one thing I wanted to mention on that is that we use Cambian data. So we use grid projected scenarios, and we use prices from region-specific prices. So it depends on what the grid's going to look like in the future. So we try to project out wholesale prices and then guess at retail rates at that point. It's really challenging, obviously, as folks probably know on this call, to track down retail rates or project retail rates. It's really up to the utilities to set those.
Yes. And someone here asks about seawater desalination, and I think it hints at a larger topic, to be honest, which is the topic of water and whether water is a big deal and is something that people should care about. And, you know, this has appeared to me. I work quite internationally in Europe, in the US, in Latin America, and in some regions it seems more important than others. It seems like water rights are a massive deal in the US. Is this a large cost? Is it a large consideration? Is it part of the planning?
Absolutely. Yeah. It is part of our modeling as well, desalinization. And right now the desalinization process is peanuts in compared to the rest of the process, but that is for onshore water. Right now we just take a flat tap water cost for accessing water, but we do have that lever to change in the future. So if you have a more complicated water structure in your area, you could add that as an input to the desalinization model. We haven't looked explicitly on, well, we have a desalinization for offshore as well, but we haven't included like disposal of brine or anything like that to make sure that the seawater in the area that doesn't become unlivable or something like that. Something crazy. There are other options too, like making hydrogen directly from seawater too. That would be cool to investigate as well.
Okay, there is, I know that we're just under, if you just give me 2 minutes and just a couple more questions and then, you know, we can leave it for today. One of them is, was asking about whether you're looking into electrolysis at all. Electrolysis dates back to 1833, according to this, I'm not really sure. It says it's time for a new solution. So what are you guys working on?
That's a good question. We are open to lots of different hydrogen production approaches. Right now, we are leaning on our hydrogen experts and material scientists at NREL to look at those types of solutions. So we are not the experts on different methods to generate hydrogen, but we can put you in touch for sure. We have that research.
Excellent. No, I know you guys aren't, but I in the NREL, there are teams, right, that are looking at that. So yeah, I would love to be in touch with them also because, and I insert here a little bit of publicity, sorry. We have a free to attend workshop in 2-3 weeks that is just focusing on electrolyzers, new current technology, future technology, bankability, all of that. So you're welcome to attend. Lucia, please, if you can put the link so that people can sign up, that'd be great. And then there is like 3-4 questions at least about storage. They talk about, carbon. I mean, you did refer much to the costs and, of storing it in caverns, in ammonia. Do you have any idea, or can you help in any way? Have you done any studies as to what is more cost competitive or it makes more sense? And this would be the last question for today.
Yes, we can really briefly touch on that. So our salt caverns were our cheapest option compared to our compressed gas, which is about 20x the cost, maybe 40x the cost. And so we looked at various technologies in between. One of the big up and coming areas is liquid organic carriers, like ammonia, for example. And so we definitely have our eye on that, especially because there's a lot more work, I guess, around ammonia safety and that kind of thing at a large scale. So we definitely have our eye on that. The biggest thing is the fact that when you convert it to ammonia, then you have to convert it back to hydrogen. So there's an extra step that makes it challenging, but it does maybe solve the transport problem potentially if we're not able to build a lot of pipelines, which is definitely possible. So keeping that option on the table. One anecdote I would say is that from our research, what Matt was showing with the Texas example, off-grid salt caverns were our lowest, but it was cost competitive with SMR, with policy in particular. And so in order to keep that cost competitiveness, storage can really only go up by 4x. So 4x salt caverns, 4 times the cost, 4 to 5 times the cost. You could still be cost competitive with SMR in good regions like good wind, solar, and hydrogen storage regions. So I just want to put that out there as like a rule of thumb, maybe, that we're starting to see. This is preliminary results, so this could change in the future, but it's not going to be 20 or 40 times X, so 40X times the cost of salt caverns. So we definitely need our eye on that to make these solutions work.
Okay, so thank you very much, Jen, for helping out with the questions and for everything else, because you've been working on this for a very long time, for also helping us out. Thank you very much, Matt, for the wonderful presentation. And I think I've saw already that you got Jen's details, you got Matt's details. This is the point of the webinars. 1 is the information, 2 is the connection with other people that are doing the stuff that you need answers to. So please get in touch with these guys if you have anything. And remember, these guys are going to be at the event. Please do come, join us, Las Vegas, in April. And also in the meanwhile, remember this workshop that is free to attend for electrolysis, and that I'm hoping also that the NREL can add value there, because you can get like in one screenshot, I think you'll get like access to a lot of information from a lot of different manufacturers. So I think that's very interesting. And without further ado, I thank you both. Matt, thank you very much, Jen, for everything, for all the support, and to you guys on the other side. And I will see you next time. So thank you very much.